Astronomers monitoring the outer solar system are growing increasingly uneasy, not because of a sudden event, but because recent calculations suggest something might have changed. After a subtle yet consequential interaction near Jupiter, the interstellar object 3I Atlas may no longer be following the straightforward outbound trajectory originally expected. No official statements have been issued, and no conclusions have been finalized, but the tone of the analysis has shifted. Orbital solutions that once aligned are beginning to diverge. Where there was confidence, there is now caution. Where the path once seemed settled, it is now defined by margins of error and unresolved sensitivities. In orbital dynamics, this is often the point where assumptions are re-examined and where unexpected outcomes become possible. Jupiter is not just another planet, it is the solar system's dominant gravitational force after the Sun, a massive gatekeeper capable of reshaping the destiny of passing bodies with even a distant encounter. When an object moves through Jupiter's sphere of influence, the exchange of energy can be profound. A slight adjustment in speed or angle near the gas giant can translate into a radically different future path over years or decades. In the case of 3I Atlas, recent orbital recalculations have raised the possibility that such an interaction may have nudged the object onto a trajectory that no longer points cleanly away from the inner solar system. The idea that it could be redirecting or even returning in some form toward Earth's neighborhood remains speculative. But speculation, when grounded in mathematics and observation, has a way of demanding attention. What makes this moment particularly compelling is not a single dramatic data point, but the accumulation of small irregularities that resist easy explanation. Astronomers are accustomed to uncertainty, especially when dealing with interstellar visitors observed over limited windows of time. Yet 3I Atlas has repeatedly pushed against expectations in ways that feel persistent rather than random. Its motion, its activity, and its geometry have all invited closer scrutiny. Each new observation seems to add complexity rather than resolve it, and each refinement of its orbit introduces new sensitivities to forces that were once considered negligible.
Does this have any steering mechanism that you think, are you seeing it go off a straight line at all? Or is there any detection that it is being steered?
That's an excellent question. So far, no data was reported about the trajectory and how close it is to what we expect from gravity alone. The data will get better as it comes closer, but eventually, yes, this is considered to be non-gravitational acceleration, a subject that could reveal the existence of a propulsion system or some engine to the object. That will definitely be a technological signature.
Is it traveling faster than what we would expect? I think, what is it, 41 miles per second? Is that faster than what we can do?
The object's behavior near the Sun intensified this attention. As it approached perihelion, the point of closest approach to the Sun, 3I Atlas experienced a measurable gravitational deflection. Such deflections are normal. Gravity bends paths all the time. What stood out here was the magnitude and the context. The object's trajectory was altered by about 16 degrees, a noticeable shift that required precise modeling to account for. Around the same time, observers noted a remarkably narrow, well-collimated jet extending in a sunward direction. This alone was unusual. Most active objects develop tails that stream away from the Sun, driven by solar heating and radiation pressure. A persistent jet pointing toward the Sun challenges that basic picture. This is where the analysis of Harvard astrophysicist Avi Loeb enters the discussion.
We see more than 7 jets that are tightly collimated coming out of this object.
Loeb drew attention not just to the presence of the sunward jet, but to its geometry. The opening angle of this jet, when measured, appeared to closely match half of the gravitational deflection angle experienced at perihelion. In other words, the numbers lined up in a way that felt more than coincidental. Geometry in celestial mechanics is rarely poetic. When angles align, they usually do so for a reason. Whether that reason is physical, structural, or something not yet fully understood remains an open question. The jet itself behaved in ways that deepened the mystery. It was not a fleeting burst or a chaotic plume. It appeared narrow, sustained, and stable over time, persisting both before and after perihelion. This persistence is difficult to reconcile with standard models of volatile-driven activity, which tend to produce broader, more variable outflows that evolve rapidly as solar heating changes. The directionality of the jet also remained remarkably consistent, maintaining its sunward orientation despite the object's changing position and velocity. Such stability suggests a mechanism that is either finely tuned or fundamentally different from what is typically observed. Beyond the jet, the object's overall geometry raised additional questions. Its orientation relative to the plane of the solar system appeared unusually aligned. While random interstellar arrivals should display a wide range of inclinations and orientations, 3I Atlas seemed to move in a way that minimized its tilt relative to the ecliptic. On its own, this would be a statistical curiosity. Combined with other anomalies, it becomes part of a pattern that invites deeper examination. Patterns, of course, can be deceptive. Humans are exceptionally good at finding meaning in coincidences. But science advances by testing whether coincidences persist under scrutiny, and in this case, they have not easily dissolved. The physical properties inferred from ongoing observations added yet another layer of complexity to an object that already defied easy classification. Despite clear signs of activity, 3I Atlas did not exhibit the chemical or visual signatures typically associated with bodies rich in common volatile ices. Instruments failed to detect the strong, chaotic outgassing patterns normally seen when such objects approach the inner solar system. Instead of broad plumes or rapidly evolving tails, its behavior appeared restrained, almost selective. The acceleration measured along its path could not be cleanly tied to the usual sublimation-driven forces that dominate most active interstellar or cometary bodies. What emerged instead was the suggestion of a more controlled or constrained transfer of momentum, one that did not align neatly with established models. This discrepancy has pushed researchers to consider alternative explanations that remain physically plausible but fall outside routine expectations. One line of reasoning proposes that 3I Atlas could possess an unusually asymmetric structure, with a geometry capable of focusing energy release into a narrow, stable region rather than dispersing it broadly. In such a configuration, even modest activity could produce sustained thrust in a preferred direction, accounting for the observed jet behavior without requiring large quantities of conventional volatiles. Another possibility involves materials that respond to solar heating at temperatures different from those commonly assumed, producing propulsion without generating the familiar observational markers typically used to diagnose activity. These mechanisms do not violate known physics, but they challenge assumptions about how interstellar objects should look and behave when exposed to solar radiation. What makes these explanations uncomfortable is not their improbability, but their cleanliness. Natural processes, especially in small bodies shaped by billions of years of collisions, radiation, and thermal cycling, tend to be irregular. Jets flicker, tails fluctuate, activity waxes and wanes unpredictably. Yet the features observed in 3I Atlas appeared persistent and coherent over time. This consistency is difficult to dismiss and even harder to fully explain. It suggests either an unusually well-organized physical structure or a set of conditions that happen to align with remarkable precision. In either case, the object resists being reduced to a single familiar category. The attention surrounding 3I Atlas has grown precisely because these characteristics refuse to collapse into a comfortable explanation. Each anomaly, when considered alone, can be rationalized. A narrow jet might be a transient feature. A lack of common volatiles could reflect observational limits. A slight deviation in acceleration could be attributed to modeling uncertainties. But when these features are taken together, they form a pattern that continues to draw scrutiny. This cumulative effect is what keeps the object under close watch, and why even cautious discussions of possible trajectory sensitivity near Jupiter are treated seriously. When an object already known for pushing the boundaries of expectation passes through the gravitational domain of the solar system's largest planet, even small uncertainties take on outsized significance. It is crucial to separate observation from interpretation. No credible analysis has shown that 3I Atlas poses a danger. There is no confirmed prediction of an Earthward approach, nor any evidence that the object is on a collision course with the inner solar system. The idea of redirection arises from sensitivity studies and evolving orbital solutions, not from a single dramatic calculation. But scientific practice does not wait for certainty before paying attention. It responds to signals, especially when complex systems are involved. Orbital dynamics are inherently nonlinear, and Jupiter's gravitational influence is one of the most powerful variables in that system, capable of magnifying subtle differences into divergent long-term outcomes. As monitoring continues and additional data refine existing models, some of the tension surrounding 3I Atlas may well dissolve. The jet may eventually be traced to an ordinary physical process. The apparent geometric coincidences could fade under statistical scrutiny. The trajectory could settle decisively onto a path that carries the object out of the solar system, never to return. This outcome remains not only possible, but probable. Yet probability alone does not explain why 3I Atlas continues to command attention. It does so because it consistently occupies the narrow boundary between what is expected and what is merely assumed. In astronomy, moments of genuine discovery rarely announce themselves with certainty. They emerge instead from discomfort, from data that almost fits, from explanations that work until they don't quite. They arise when patterns persist just long enough to resist dismissal, but not long enough to be explained away. 3I Atlas exists squarely in that space. Whether it ultimately fades into obscurity as another unusual interstellar visitor or forces a reassessment of how such objects behave remains unresolved. For now, it continues its passage through the solar system, shaped by gravity, radiation, and forces still being unraveled, serving as a reminder that even in a domain governed by precise laws, not every path is immediately predictable.